Right now, as you sit there reading these words, 100 trillion neutrinos are passing through your body every single second. They stream through your skin, through your bones, through every atom you are made of. They pour through the chair beneath you, through the floor, through the foundation of the building, through bedrock and mantle, and the molten iron core of the Earth itself. They emerge on the other side of the planet without slowing down, without being deflected, without interacting with a single atom in the entire 12,700-kilometer journey through solid matter. Not one of them will touch you. Not one. In your entire lifetime, out of the trillions upon trillions that will fly through you, maybe just one will ever make contact with an atom inside your body. This is the story of the particle that barely knows you exist. And the man who spent 30 years proving it was real. Let me start with something you already understand without thinking about it. You can touch things. You pick up a glass of water and you feel it in your hand. You press your fingers against the table and the table pushes back. You step on the ground and the ground holds you up. This seems obvious. This seems like the most basic, unremarkable fact about reality. But it is actually extraordinary. Understanding why you can touch things is the first step toward understanding why neutrinos cannot. Everything around you, the chair you are sitting in, the device you are reading from your body, the air in the room is made of atoms. Atoms are the building blocks of all ordinary matter. Every element on the periodic table is defined by its atoms. Hydrogen, the simplest element, has 1 proton and 1 electron. Carbon, the basis of all life on Earth, has 6 protons, 6 neutrons, and 6 electrons. Iron, the element that makes up most of Earth's core, has 26 protons, 30 neutrons, and 26 electrons. There are 92 naturally occurring elements, each with a different number of protons in its nucleus. Each with different properties, all of them built from the same 3 basic components: protons, neutrons, and electrons. An atom has 2 main parts. At the center is the nucleus, a dense clump of protons and neutrons packed together incredibly tightly. Surrounding the nucleus at a much greater distance are the electrons. Now here is what is remarkable. The nucleus is tiny, unimaginably tiny compared to the atom as a whole. If you enlarged an atom to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. The electrons would be like gnats buzzing around the outer seats. Everything in between would be empty space. This means that matter, the stuff you think of as solid, is overwhelmingly nothing. Your body, which feels so substantial, is almost entirely empty space. The atoms that make you up are almost entirely empty space. If you could somehow remove all the empty space from every atom in every human being on Earth, all 8 billion of us, the remaining matter would fit in a volume smaller than a sugar cube. All of humanity, a sugar cube of actual material. The rest is void. So if atoms are mostly empty space, why does the world feel solid? Why can you not walk through walls? The answer has nothing to do with physical material blocking. Physical material. It is because of a force, a fundamental force of nature. And that force is the electromagnetic force. When you press your hand against a table, the electrons surrounding the atoms in your skin repel the electrons surrounding the atoms in the table surface. This electromagnetic repulsion creates a barrier that your hand cannot penetrate. Nothing is actually touching in the way you intuitively imagine. It is all forces, all fields, all electromagnetic interactions at a distance. The solidity of everything you have ever touched is an electromagnetic illusion. Real in its effects, but fundamentally a product of charged particles pushing against each other across empty space. This leads us to something essential. The universe operates through 4 fundamental forces. Just 4. Every interaction between every particle in the entire cosmos is governed by one or more of these 4 forces. Understanding them is critical to understanding neutrinos, because what makes neutrinos so extraordinary is which of these forces they respond to and which they ignore entirely. The first force is gravity. Gravity is the one you know best. It is the force that keeps your feet on the ground, that keeps the Earth in orbit around the sun, that holds galaxies together. Gravity acts on anything that has mass or energy. It has infinite range. It reaches across the entire observable universe. The sun's gravity holds Neptune in orbit at a distance of 4.5 billion kilometers. The Milky Way's gravity holds its hundreds of billions of stars together across a span of 100,000 light years. But here's the thing about gravity that most people do not appreciate. It is weak. Incredibly, almost absurdly weak. It seems strong because you are standing on a planet with a mass of about 6 trillion kilograms, and all that mass is pulling you down. But the gravitational attraction between two individual subatomic particles is essentially nothing. The gravitational pull between two protons is roughly 10 to the 36th power times weaker than the electromagnetic force between them. That is a 1 followed by 36 zeros. Gravity matters at cosmic scales because it always attracts. It never cancels out. It adds up over enormous amounts of matter. But at the scale of individual particles, gravity is irrelevant. It is the weakest force in the universe by an almost incomprehensible margin. The second force is the electromagnetic force. This is the force that actually governs your daily life far more than gravity does, even if you do not realize it. The electromagnetic force acts between particles that carry electric charge. Protons carry positive charge. Electrons carry negative charge. Opposite charges attract, like charges repel. This is the force that holds atoms together. The positive protons in the nucleus attract the negative electrons, keeping them bound in their orbits. It is the force that holds molecules together through chemical bonds. It is the force responsible for all of chemistry and all of biology. When you see light, you are detecting electromagnetic radiation. When you listen to a radio, you are picking up electromagnetic waves. When your nerve cells fire, they are using electromagnetic signals, every color. Every sound your ears convert from pressure waves transmitted through electromagnetically bonded air molecules. Every sensation of touch or heat, all of it is electromagnetic. This force has infinite range like gravity, but it is vastly stronger at the particle scale. The electromagnetic force is what makes the world tangible. It is the reason things feel real. The third force is the strong nuclear force, sometimes just called the strong force. This is the most powerful force in the universe, but it operates over an incredibly short range, only about the width of an atomic nucleus. Roughly 10 to the negative 15th meters. That is about 1/quadrillionth of a meter. Beyond that distance, the strong force effectively ceases to exist. The strong force is what holds the nucleus together. Think about this for a moment. Protons are all positively charged. They should repel each other electromagnetically. A nucleus with two or more protons should fly apart instantly because of the electromagnetic repulsion. But it does not, because the strong force overpowers the electromagnetic repulsion at these tiny distances. The strong force binds quarks together to form protons and neutrons, and it binds those protons and neutrons together to form nuclei. Without it, no nucleus heavier than hydrogen could exist. There would be no carbon, no oxygen, no iron, no rocky planets, no life. The strong force is the reason matter has the complexity it does. And then there is the fourth force, the weak nuclear force. This is where our story truly begins. The weak force is unusual compared to the other three. It does not hold anything together. It does not attract particles to each other the way gravity and electromagnetism do. It does not bind structures the way the strong force does. Instead, the weak force is responsible for transformation. It allows one type of particle to change into another type. The weak force is what drives a specific kind of radioactive decay called beta decay, where a neutron inside a nucleus transforms into a proton, emitting an electron, and as we will discover, a neutrino in the process. The weak force operates over an even shorter range than the strong force. Its effective range is about 10 to the negative 18th meters, roughly 1,000 times smaller than the diameter of a proton. If a proton were the size of a city, the weak force would reach across a single room inside one building. The weak force is also true to its name, much feebler than both the strong force and the electromagnetic force at the particle scale. It is stronger than gravity between individual particles, but compared to the other two forces that govern atomic and nuclear physics, it is remarkably feeble. Now here is the crucial point. Different particles respond to different forces. What determines how a particle behaves, how it interacts with the world around it, is which forces it feels. Protons feel all four forces. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They contain quarks, so the strong force acts on them. And they participate in weak interactions. Protons are thoroughly sociable particles. They interact with everything. Electrons feel three of the four. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They participate in weak interactions. But they do not contain quarks, so the strong force does not act on them directly. Still, 3 out of 4 forces is plenty. Electrons interact readily with the world. And then there are neutrinos. Neutrinos are in a category almost by themselves. They have a tiny amount of mass, so technically gravity acts on them. But their mass is so minuscule that this gravitational interaction is utterly negligible for any practical purpose. They have no electric charge whatsoever. Zero. This means the electromagnetic force, the force that governs almost everything in your daily experience, the force responsible for chemistry, biology, light, and the solidity of matter simply does not apply to neutrinos. They are blind to it. They also do not contain quarks, so the strong nuclear force has no hold on them either. The only force through which neutrinos can meaningfully interact with other matter is the weak nuclear force, the one force with the shortest range and the lowest interaction probability. This single fact is why neutrinos are ghosts. The story of how we came to know about neutrinos begins with a crisis in physics. In the early 20th century, physicists were carefully studying beta decay. In this process, a radioactive nucleus emits an electron and transforms into a different element. For example, a carbon-14 nucleus decays into nitrogen-14. One of its neutrons has turned into a proton and an electron flies out. The problem was energy conservation. The total energy before a reaction must equal the total energy after. This is one of the most fundamental laws in all of physics. It is not a suggestion. It is not an approximation that works most of the time. It is an absolute rule verified in every experiment ever conducted, a cornerstone of the entire edifice of physics. If energy conservation fails, almost everything we know about the universe comes into question. But when physicists precisely measured the energy of the electrons emitted in beta decay, they found something deeply disturbing. The electrons did not all come out with the same energy. They had a continuous spectrum of energies, ranging from nearly zero up to some maximum value. This was wrong, profoundly wrong. If a specific nucleus decays into a specific product nucleus and emits one electron, the energy balance should be exact. The starting energy is fixed. The ending energy is fixed. The electron should carry away the difference, always the same amount every single time. But measurement showed otherwise. Some electrons came out fast, carrying nearly all the available energy. Others came out slow, carrying barely any. And everything in between, a smooth, continuous distribution of energies. It was as though the universe were randomly deciding for each individual decay how much energy to give the electron. Sometimes a lot, sometimes a little, with no apparent pattern or reason. The implications were alarming. If the electron was carrying less than the full available energy, where was the rest going? Physicists checked for gamma rays, high-energy photons that might be carrying away the missing energy. They found none. They checked for recoil energy in the nucleus itself. The numbers did not balance. No matter how carefully they measured, no matter how precisely they accounted for every form of energy they could think of, there was always some energy unaccounted for. It simply vanished. The books did not balance. And in physics, the books must always balance. This was a genuine crisis in the foundations of physics, not a minor discrepancy, not a measurement artifact, but a fundamental challenge to one of the most sacred principles in all of science. Some brilliant physicists, including Niels Bohr, one of the fathers of quantum mechanics, suggested that perhaps energy conservation simply did not hold at the subatomic level. Maybe it was only an approximate rule valid statistically for large collections of atoms, but not for individual nuclear reactions. Bohr was willing to abandon conservation of energy. That is how serious the problem was. When one of the greatest physicists in history is prepared to throw out one of the most fundamental laws in physics, you know the situation is desperate. One physicist in particular found this idea intolerable. Wolfgang Pauli, an Austrian theoretical physicist known for his extraordinary intellect and his famously sharp tongue. He once dismissed a colleague's theory as not even wrong, meaning it was too vague to be tested. Pauli refused to abandon energy conservation. In December of 1930, Pauli wrote a now famous letter to a group of physicists attending a conference in Tübingen, Germany. He addressed them as, "Dear radioactive ladies and gentlemen," and proposed what he called a desperate remedy. He suggested that during beta decay, alongside the electron, another particle was being emitted. A particle so elusive, so reluctant to interact with anything that no instrument could detect it. This particle, Pauli argued, carried away the missing energy. It had to be electrically neutral because the electric charge is already balanced without it. It had to have very little mass, possibly none, because the maximum energy of the emitted electrons nearly accounted for all the available energy. And it had to interact extraordinarily weakly with matter because nobody had ever seen any trace of it. Pauli initially called this hypothetical particle a neutron. But that name was soon claimed by the much heavier neutral particle James Chadwick discovered inside atomic nuclei in 1932. The Italian physicist Enrico Fermi then renamed Pauli's particle the neutrino, which in Italian means little neutral one. But Fermi did far more than just name it. In 1933 and 1934, he developed a comprehensive theoretical framework for beta decay that incorporated the neutrino and described how the weak force operated. His theory explained how a neutron could transform into a proton while emitting an electron and a neutrino. It was elegant, mathematically precise, and turned out to be remarkably accurate, but it depended entirely on a particle that no one had ever directly observed. The challenge was stark. How do you detect a particle that barely interacts with anything? Pauli himself was deeply pessimistic. He reportedly bet a case of champagne that his particle would never be found. He later said he had committed a terrible thing by proposing a particle that could never be observed experimentally. And for a long time it seemed like he might be right. The years stretched on. The 1930s passed. Fermi's theory gained acceptance because it explained beta decay so well. But the neutrino at its heart remained invisible. The 1940s came and went, a decade dominated by war and the development of nuclear weapons. Work that deepened understanding of nuclear reactions, but brought physicists no closer to catching Pauli's ghost. The technology simply did not exist. Detecting a particle with such an absurdly small interaction probability required either an incredibly intense source of neutrinos or an incredibly massive detector, or both. In the 1930s and 40s, neither was available. This is complex because reality is complex. You're understanding it correctly. The numbers are not abstractions. They are predictions we can test. And we will. By the early 1950s, the situation had changed. Nuclear reactors developed as part of the Cold War nuclear programs provided exactly the kind of intense neutrino source that was needed. A nuclear reactor is essentially a controlled chain reaction of uranium fission. Each fission event produces several neutron-rich fragments that undergo beta decay. And each beta decay produces a neutrino, or more precisely, an anti-neutrino. A large reactor produces an almost inconceivable number of these particles. The flux near a powerful reactor core reaches roughly 10 trillion antineutrinos per square centimeter per second. That is an enormous number of neutrinos concentrated in a relatively small area. If you could put a big enough detector close enough to a reactor, statistics might finally work in your favor. Even with a probability of interaction close to zero for any individual neutrino, the sheer torrent of particles might produce a few detectable events. Two American physicists saw this opportunity and seized it. Frederick Reines and Clyde Cowan designed an experiment to detect antineutrinos produced by the Savannah River nuclear reactor in South Carolina. Their approach relied on a process called inverse beta decay. On extremely rare occasions, an antineutrino would interact with a proton in a tank of water via the weak force converting the proton into a neutron and producing a positron, the antimatter counterpart of the electron. The positron would immediately annihilate with a nearby electron, creating two gamma rays flying off in opposite directions. The neutron would bounce around briefly before being captured by a cadmium nucleus dissolved in the water, which would then emit its own distinctive gamma rays after a brief delay. These two bursts of gamma rays, separated by a tiny but measurable time gap of a few microseconds, created a unique signature, a double pulse of light with a specific timing pattern that could be distinguished from random background events. It was a masterpiece of experimental design. The double pulse signature was the key. Random background events could produce a single gamma ray easily enough, but producing two gamma ray bursts with exactly the right energies separated by exactly the right time delay was something that almost only a genuine anti-neutrino interaction could do. This gave Reines and Cowan a way to pick out the incredibly rare signal from the overwhelming background noise. Months of painstaking data collection followed. Background noise had to be carefully measured and subtracted. Every possible source of false signals had to be accounted for. They ran the experiment with the reactor on and with the reactor off. If the signal was really from reactor neutrinos, it should appear when the reactor was running and vanish when it was shut down. And that is exactly what they found. The signal was there, clear, consistent, and unmistakable. It appeared when the reactor was on and disappeared when the reactor was off. The ghost had been caught. Reines and Cowan sent a telegram to Wolfgang Pauli with a simple message: "We are happy to inform you that we have definitely detected neutrinos." Pauli was reportedly overjoyed. He shared the telegram with his colleagues at a conference in Zurich and drank the champagne he had wagered against this very outcome. The particle he had proposed out of desperation 26 years earlier, the particle he feared could never be found, had been observed. Energy conservation was saved. The desperate remedy had been real all along. 26 years, from crisis to theory to detection. You have followed a journey because the physicists were patient with reality, depth over speed, understanding over speculation. But catching the ghost from a reactor was one thing. Catching neutrinos from the sun, 93 million miles away, that would require something else entirely. It would require a man willing to be wrong for 30 years. His name was Raymond Davis Jr., an American chemist with an extraordinary talent for precision measurement and an almost superhuman patience. In the mid-1960s, Davis constructed an experiment deep inside the Home State Gold Mine in Lead, South Dakota, about 1,470 meters underground. The mine had been in operation since the 1800s. Its tunnels bored deep into the Black Hills of South Dakota in search of gold. Davis was not looking for gold. He was looking for something far more elusive, evidence that neutrinos from the sun's core were reaching Earth and occasionally, against all odds, interacting with matter. The heart of his experiment was a tank containing roughly 615 metric tons of perfluoroethylene, ordinary industrial dry cleaning fluid. This is not what you might picture when you think of a cutting-edge physics experiment. There were no gleaming instruments, no blinking panels of electronics. It was essentially a very large cylindrical vat of solvent sitting in a cavern carved out of rock connected to some pumping equipment and chemical extraction apparatus. It was unglamorous to the point of being almost absurd. Visitors to the mine who saw it for the first time were sometimes baffled. This was supposed to detect particles from the sun, a tank of cleaning fluid in a hole in the ground, but its design was brilliant. The choice of material was not arbitrary. It was the product of careful theoretical calculation about which nuclei would be most sensitive to the particular energies of solar neutrinos. Perchloroethylene contains chlorine, and specifically the isotope chlorine-37, which makes up about 1/4 of all natural chlorine. On extraordinarily rare occasions, a solar neutrino would interact with a chlorine-37 nucleus through the weak force, transforming it into an argon-37 nucleus and emitting an electron. This reaction, called the inverse beta decay of chlorine-37, was the detection mechanism. Each time it occurred, one atom of chlorine-37 would become one atom of argon-37. Davis's job was to count the argon atoms. Pause and consider the absurdity of this task. He had 615 metric tons of fluid. That is roughly 2,380,000 liters. In this enormous volume, the sun's neutrino flux was predicted to produce, on average, roughly 1 or 2 argon-37 atoms every single day. 1 or 2 atoms per day in 615 tons of liquid. It would be like trying to find one specific grain of sand that had been secretly added to a swimming pool full of sand. Except the grain is an atom, and the swimming pool is the size of a small building. Finding it required chemical techniques of extraordinary sensitivity, the kind of work that demanded not just scientific knowledge, but something closer to artistry. Davis had to extract individual atoms from a sea of trillions of trillions. Davis ran the experiment in cycles lasting several weeks. He would let the detector sit undisturbed, quietly accumulating argon atoms from the rare neutrino interactions. Then he would flush helium gas through the entire tank, which would carry the tiny number of volatile argon atoms out of the liquid. He would collect the helium, extract the argon through painstaking chemical separation, and place the argon sample in a small proportional counter, a device that could detect the radioactive decay of individual argon-37 atoms as they converted back to chlorine-37. By counting these decays over a period of months, he could determine how many neutrino interactions had occurred during the exposure period. Each complete measurement cycle, from closing the tank to flushing it, extracting the argon, purifying it, and counting the decays, took the better part of a year. The statistical uncertainties were large because the numbers were so small. A handful of atoms here, a handful there. Davis needed many cycles, many years of data to build up enough statistics to say anything definitive. He ran the experiment for nearly 3 decades. 3 decades of cycling the same tank, flushing the same helium, extracting the same infinitesimal quantities of argon, counting the same faint radioactive decays. It was science at its most patient and most demanding. Davis spent more time with that tank of cleaning fluid than most people spend in any single career. He began the experiment as a middle-aged scientist and was still running it as an elderly man. And then the results came in, and they were puzzling. Davis did find argon atoms, definitive proof that solar neutrinos were reaching his detector and occasionally interacting. The experiment worked. The neutrino Pauli's ghost particle was being caught in a vat of dry cleaning solvent a mile underground. But Davis found only about 1/3 as many argon atoms as theorists had predicted. Solar models built on our understanding of nuclear fusion in the sun's core predicted a certain rate of neutrino interactions based on the temperature, density, and composition of the solar interior. Davis was measuring roughly a third of that predicted rate. Two-thirds of the expected neutrinos appeared to be missing. This discrepancy became known as the solar neutrino problem, and it was one of the most stubborn and perplexing puzzles in physics for the next 30 years. It gnawed at the field. It divided physicists into camps. It spawned hundreds of theoretical papers, dozens of proposed explanations, and years of heated debate at conferences around the world. Because the discrepancy struck at something fundamental. Either we did not understand how the sun works, which would mean our models of stellar physics were deeply flawed, or we did not understand neutrinos, which would mean our standard model of particle physics was incomplete. Both possibilities were deeply uncomfortable. Both had enormous consequences. The stakes were high because the solar model was not just some rough sketch. It was one of the most carefully constructed and thoroughly tested models in all of astrophysics. Decades of work had gone into understanding stellar interiors, the temperatures, pressures, densities, energy, transport mechanisms, nuclear reaction rates, and compositions. The solar model successfully predicted the sun's luminosity, its radius, its surface temperature, and the frequencies of its oscillation modes, which had been measured with extraordinary precision by helioseismology. It was not a model that seemed likely to be wrong by a factor of 3, and yet Davis kept getting the same answer. Year after year, cycle after cycle, he extracted his argon atoms and counted them, and the number was always about one-third of what the theorists said it should be. Some physicists questioned his methods. Some wondered if his chemical extraction was inefficient, if he was losing argon atoms during the process and undercounting. Davis tested this by injecting known quantities of argon into his tank and extracting them. He consistently recovered more than 90%. The extraction was working. The deficit was real. Other physicists scrutinized the solar models. Maybe the core temperature was slightly lower than calculated. A small change in temperature could significantly affect the rate of certain fusion reactions, and thus the neutrino production rate. Solar physicists examined this possibility, meticulously adjusting parameters, refining their inputs, testing sensitivity to various assumptions. The models were robust. You could tweak parameters within their allowed ranges and reduce the predicted neutrino rate somewhat, but not by a factor of 3. The discrepancy persisted stubbornly, no matter how you adjusted the model within reasonable bounds. The solar neutrino problem became a slow-burning crisis, not an explosive controversy, but a persistent, nagging wound in the body of physics that would not heal. For 30 years, it sat there defying resolution. Davis kept running his experiment. Theorists kept arguing, and the missing neutrinos refused to be found. This is frustrating. It was frustrating for physicists too. Major questions do not resolve quickly. Patience is not just a virtue, it is a method. There were several possible explanations, and physicists debated them vigorously. Maybe the nuclear physics inputs were wrong. Perhaps the cross-sections of certain nuclear reactions in the sun had been measured incorrectly in laboratory experiments. Physicists revisited these measurements, improving their precision with better accelerators and better detectors. The results tightened the predictions somewhat, but did not resolve the discrepancy. Or maybe, and this was the most radical and exciting possibility, something was happening to the neutrinos themselves during their 8-minute journey from the sun to Earth. Maybe they were changing, transforming, becoming something that Davis's detector could not see. Here is the key. Davis's chlorine detector was only sensitive to electron neutrinos. That is the flavor produced in the sun's fusion reactions. If some of those electron neutrinos were transforming into muon neutrinos, or tau neutrinos, during their journey from the sun to Earth, they would still arrive at the homestake mine. They would still pass through the tank of perchloroethylene, but they would be invisible to the chlorine-37 reaction, which only responds to electron neutrinos. They would be there, but Davis could not see them. This idea that neutrinos could spontaneously change from one flavor to another during flight is called neutrino oscillation. It was first proposed in the late 1950s by the Italian-Russian physicist Bruno Pontecorvo. According to quantum mechanics, if the 3 neutrino flavors have slightly different masses, then something strange happens. A neutrino produced as a pure electron. Neutrino is actually a quantum superposition of 3 mass states. As the neutrino travels through space, these mass states evolve at slightly different rates because they have slightly different masses. The result is that the probability of the neutrino being detected as an electron neutrino varies with distance. It oscillates. At some distances, the neutrino is mostly electron flavor. At other distances, it is mostly muon or tau. It is a purely quantum mechanical effect, a consequence of the wave nature of matter. and it has no analogy in everyday experience. But for neutrino oscillation to work, neutrinos must have mass. If all three flavors were massless, as the standard model of particle physics had originally assumed, the mass states would all be identical. There would be no differential evolution and no oscillation would occur. The fact that Davis was seeing fewer electron neutrinos than expected was a tantalizing hint that neutrinos might not be massless after all. But a hint is not proof. It took decades and two entirely different experiments on opposite sides of the Pacific Ocean to provide definitive evidence. Raymond Davis spent 30 years being told his results were wrong, 30 years of colleagues questioning his methods, his competence, his sanity, 30 years of counting argon atoms in a hole in the ground while the world moved on. But he never stopped. He believed in his measurements. He believed in his extraction efficiency. He believed in the integrity of his work. And he was right. He was right the entire time. The numbers were perfect. The deficit was real. The solar neutrinos were not missing. They were just wearing different costumes. And proving that would require detectors that could see all the disguises. Detectors that would not exist for another 40 years. But they would come. And when they did, Raymond Davis, 88 years old, white-haired, bent, but unbroken, would stand on a stage in Stockholm and receive the Nobel Prize in Physics for being right when everyone said he was wrong, for 30 years of patience, for catching ghosts in cleaning fluid, for refusing to give up on an invisible truth. The weapon that ended the war gave us the tool to catch the ghost. This is not poetic license, it is literal truth. Nuclear reactors born from the Manhattan Project, refined during the Cold War arms race, produce neutrinos in staggering quantities. The fission of uranium-235 creates neutron-rich fragments. These fragments are unstable. They undergo beta decay, and each beta decay releases an antineutrino into the world. A single large reactor produces approximately 5 times 10 to the 20th power antineutrinos every second. That is 500 billion particles streaming outward from the reactor core every single second of operation. The flux near a powerful reactor reaches 10 trillion antineutrinos per square centimeter per second, an incomprehensible torrent of invisible particles flooding the space around the facility. And this gave physicists something they had never had before, a controllable, intense, concentrated source. If you could place a detector close enough to a reactor, close enough to bathe in that flood, then even with neutrinos' absurdly small interaction, probability statistics might work in your favor. Out of trillions passing through your detector every second, maybe a few would interact. Frederick Reines understood this. An American physicist, 40 years old in 1956, tall, intense, driven by a peculiar mixture of ambition and genuine wonder. He had worked at Los Alamos during the war, contributing to the calculations that made the atomic bomb possible. The bomb haunted him. Not with guilt exactly, but with a sense of debt, as though the universe demanded that this terrible knowledge be balanced with something pure, something that served only understanding. Clyde Cowan was his partner in this redemption. Shorter, quieter, equally brilliant. An experimentalist with an almost supernatural intuition for instrumentation. Where Reines provided vision, Cowan provided precision. Together they designed the most audacious neutrino detector yet attempted. The location was the Savannah River site in South Carolina, a sprawling nuclear facility built in the early 1950s to produce plutonium and tritium for nuclear weapons. 5 reactors operating in the swamps and pine forests of the coastal plain. Reines and Cowan chose Reactor P, the most powerful, the one with the highest neutrino flux. They positioned their detector just meters from the reactor core. The detector itself was elegant in its simplicity. 200 liters of liquid scintillator, a solution that produces tiny flashes of light when struck by radiation. The scintillator was loaded with cadmium chloride dissolved in water, surrounded by photomultiplier tubes that could detect even single photons. The principle was inverse beta decay. An antineutrino enters the detector. If, against all probability, it happens to strike a proton in the water, the weak force mediates a transformation. The proton becomes a neutron. A positron is created. The positron immediately encounters an electron. Matter meets antimatter. They annihilate in a flash of pure energy, producing 2 gamma rays that fly off in opposite directions at the speed of light. The neutron, meanwhile, bounces around for a few microseconds before being captured by a cadmium nucleus. When the cadmium absorbs the neutron, it enters an excited state and then relaxes, emitting its own burst of gamma rays. 2 flashes, separated by a few microseconds, each with specific energies. This double pulse, this signature written in light, was something that almost nothing else in nature could produce. Random background radiation might create a single gamma ray. Cosmic rays, radioactive decay, and the surrounding rocks scattered photons from the reactor itself. All of these produce noise. But two gamma ray bursts with exactly the right energies, separated by exactly the right time interval in exactly the right pattern. That could only be a neutrino. Reines and Cowan began data collection in the summer of 1953. Months passed. The reactor hummed. The detector watched. Photomultiplier tubes fired constantly as background radiation peppered the scintillator. But hidden in that noise, if the theory was correct, were the faint double pulses they sought. The analysis was painstaking. Every event had to be examined. Every coincidence had to be tested. Was the timing right? Were the energies correct? Could this be explained by something other than a neutrino? Slowly, over hundreds of hours of running time, a signal emerged. Events that matched the neutrino signature. Not many, a few per hour, but consistent, repeatable, real. Still doubt lingered. How could they be certain these events were truly from neutrinos and not some subtle artifact of the detector or the reactor environment? Reines proposed the definitive test. They would run the experiment with the reactor on. Then they would shut the reactor down and run it again. If the signal was from reactor antineutrinos, it should vanish when the reactor stopped operating. If it persisted, they were measuring background. The reactor shutdown was scheduled for early 1956. For 2 weeks, reactor P fell silent. No fission, no neutron flux, no beta decay, no neutrinos. The detector kept running, and the signal disappeared, completely, unambiguously. When the reactor restarted, the signal returned. On signal present, off signal absent. On signal present, there was no room for doubt. They had caught the ghost. On the evening of June 14, 1956, Frederick Reines composed a telegram. The recipient was Wolfgang Pauli, now 66 years old, at the ETH Zurich in Switzerland. The message was brief. We are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of protons. Observed cross-section agrees well with the expected 6 times 10 to the minus 44 square centimeters. Pauli received the telegram while attending a conference. He was giving a lecture when an assistant brought him the message. He stopped mid-sentence, read it, and looked up at the audience. For a moment, he said nothing. Then he smiled, a rare expression for a man famous for his severity, and announced to the room that the neutrino proposed 26 years earlier, in a moment of desperation, had been found. That evening, he shared champagne with colleagues. The same champagne he had wagered would never need to be drunk. Wolfgang Pauli died 2 years later, in 1958. He never lived to see the deeper mysteries the neutrino would reveal. But he died knowing that his desperate remedy had been vindicated. Energy conservation was secure, the weak force was real, and the particle he thought could never be caught had been caught. 26 years from crisis to confirmation. From theoretical desperation to experimental triumph. This is how science works when it is patient, when it refuses to abandon fundamental principles, when it builds piece by piece toward truth. You have followed a journey across decades. From Pauli's letter to Reines and Cowan's detector, the pieces fit because you have been given them in order. This is how discovery actually happens. Cumulative, patient, built on the work of those who came before. But catching antineutrinos from a reactor particles produced just meters away was one thing. Catching neutrinos from the sun, 93 million miles distant, traveling through the vacuum of space for 8 minutes before arriving at Earth, that was something else entirely. That required not just a detector, but a commitment bordering on obsession. It required Raymond Davis. Davis was not like Reines or Cowan. He was not a theorist who moved between problems following wherever his curiosity led. He was a chemist, methodical, patient, stubborn in a way that bordered on mule-headedness. Born in 1914 in Washington, D.C., grew up during the Depression. Learned early that nothing came easy, that precision mattered, that shortcuts led nowhere. He earned his Ph.D. in physical chemistry from Yale in 1942, just as the war consumed the world. Spent the war years working on chemical separation techniques for the Manhattan Project. After the war, he joined Brookhaven National Laboratory on Long Island. It was there in the late 1950s that Davis became obsessed with a question. If neutrinos from reactors could be detected, what about neutrinos from the sun? The sun is a thermonuclear furnace. Deep in its core, where temperatures reach 15 million degrees Celsius and pressures are 265 billion times Earth's atmospheric pressure at sea level, hydrogen nuclei are being fused together into helium. This process, called the proton-proton chain, releases energy. That energy is what makes the sun shine, what keeps Earth warm, what makes life possible. But fusion also produces neutrinos, specifically electron neutrinos. Born in the heart of the sun, created in the same reactions that produce the light you see when you look up at the sky. The sun generates roughly 2 times 10 to the 38th neutrinos every second. 200 billion neutrinos pouring outward from the core in all directions at very nearly the speed of light. By the time they reach Earth 8 minutes and 20 seconds later, they have spread out over an enormous sphere with a radius of 150 million kilometers. But even spread that thin, the flux at Earth is staggering. About 65 billion solar neutrinos pass through every square centimeter of area facing the sun every single second. Hold up your thumbnail, roughly 1 square centimeter. 65 billion neutrinos just passed through it while you held it up. And they did not stop at your thumbnail. They continued straight through your hand, through your arm, through your body, through the chair, through the floor, through bedrock, through the mantle, through the core, through the other side of the planet, and out into space without slowing down. During the day, these neutrinos arrive from above, from the direction of the sun. At night, they arrive from below. They have already passed through the entire Earth to reach you, unceasing, eternal. An invisible flood that has been washing over this planet since the sun ignited 4.5 billion years ago. Davis wanted to count them. Not all of them. That would be impossible. But enough to verify that the sun worked the way we thought it did. Enough to test at our models of stellar fusion. Enough to prove that neutrinos from the stars could be caught. The question was how. Solar neutrinos have much lower energies than reactor antineutrinos. The inverse beta decay reaction that Reines and Cowan used would not work. The solar neutrinos simply do not carry enough energy to transform a proton into a neutron and a positron. Davis needed a different reaction, one with a lower energy threshold. He found it in chlorine, specifically chlorine-37, a stable isotope that makes up about 24% of naturally occurring chlorine. When a neutrino, if it happens to interact, strikes a chlorine-37 nucleus, the weak force can transform one of the neutrons in the nucleus into a proton. The nucleus transmutes. Chlorine-37 becomes argon-37. An electron is emitted. Argon-37 is radioactive. It decays back to chlorine-37 with a half-life of 35 days, emitting a characteristic X-ray in the process. If Davis could accumulate argon-37 atoms over weeks or months, then extract them and count their radioactive decays, he could determine how many neutrino interactions had occurred. The challenge was the numbers. Theoretical calculations predicted that a detector containing 100,000 gallons of a chlorine-rich liquid would capture roughly 1 solar neutrino per day. 1 atom per day in 100,000 gallons of liquid. Finding that single atom would require chemical extraction techniques of almost unimaginable sensitivity. Most chemists would have laughed at the idea. Some did. Davis did not laugh. He began designing the detector. He needed 3 things. First, a massive volume of chlorine-rich material. After considering various options, he settled on perchloroethylene C, 2Cl4, an industrial solvent used in dry cleaning, cheap, available in large quantities, and packed with chlorine-37 atoms. 615 metric tons of it, enough to fill a tank the size of a small swimming pool. Second, a location deep underground. Cosmic rays constantly bombard Earth's surface, producing showers of secondary particles, muons, electrons, gamma rays. These particles could mimic neutrino interactions or produce background argon through other nuclear reactions. Going underground solves this. Rock is excellent at stopping cosmic rays. Muons, the most penetrating component of cosmic ray showers, are gradually absorbed as they pass through rock, losing energy with each electromagnetic interaction. Go deep enough, and even the muon flux drops to almost nothing. The only particles that can still reach your detector at great depths are neutrinos, because neutrinos pass through rock just as easily as they pass through everything else. Third, extraordinary patience, because even with 615 tons of perchloroethylene, even with perfect shielding from cosmic rays, the capture rate would be minuscule, 1 or 2 argon atoms per day. To accumulate enough atoms to count reliably, Davis would need to run the detector for weeks at a time. To reduce statistical uncertainties to acceptable levels, he would need to repeat the measurement many times over many years. It would be a lifetime's work. Davis understood this from the beginning. He chose the Homestake Gold Mine in Lead, South Dakota, an active mine that had been operating since 1876, boring tunnels deep into the Black Hills in pursuit of gold veins. By the 1960s, some of those tunnels extended nearly a mile underground. Davis negotiated with the mining company. They agreed to let him excavate a cavern at the 4,800-foot level, about 1,470 meters below the surface. Enough rock overhead to stop essentially all cosmic rays, but transparent to neutrinos. Construction began in 1965, carving out the cavern, installing the tank, welding it together from steel plates, testing for leaks, filling it with perchloroethylene trucked in from chemical suppliers. The detector was ready for operation in 1968. Davis was 54 years old. He would run the experiment until 1994, 26 years. Longer than Pauli waited for the neutrino to be found. Longer than most careers in experimental physics. The procedure was always the same. Close the tank, let it sit undisturbed for 50 to 100 days while solar neutrinos stream through it. A tiny fraction 1 in every 10 to the 36th or so would interact with a chlorine-37 nucleus, creating an argon-37 atom. After the exposure period, flush the entire 615 tons of perchloroethylene with helium gas. The argon, being a noble gas, would be carried along with the helium. Collect the helium. Separate the argon using cold traps and selective adsorption. You are now holding perhaps 20 or 30 argon-37 atoms, if you are lucky, mixed with a much larger number of stable argon-36 and argon-38 atoms from trace contamination. Place the sample in a miniature proportional counter, a device so sensitive it can detect the decay of a single atom. Wait, watch, count. Each time an argon-37 atom decays, it emits an X-ray with a very specific energy, 2.82 kiloelectron volts. This energy signature is unique. It tells you this was argon-37, not some other isotope. Count the decays over several weeks as the argon-37 gradually disappears, decaying with its 35-day half-life. From the number of counts and the known decay rate, calculate backward to determine how many argon-37 atoms were present at the start. That number tells you how many neutrino interactions occurred during the exposure period. Each cycle exposure, extraction, counting analysis took 4 to 6 months. The statistical uncertainties were large because the numbers were so small. Sometimes you would count 15 argon-37 decays, sometimes 8, sometimes 23. The Poisson statistics of small numbers made every measurement noisy. To say anything definitive, Davis needed many cycles, many years, many extractions. He settled into a rhythm, a routine that would define the next 3 decades of his life. Open the tank, close the tank, wait, flush, extract, count, calculate, publish, repeat, year after year, in a cavern carved from rock a mile underground. In the Black Hills of South Dakota, far from the major centers of physics research, far from the spotlight of scientific fame, just Davis and his tank and the invisible neutrinos streaming down from the sun. The first results came in around 1970. Davis found argon-37. The solar neutrinos were real. They were reaching Earth. They were interacting just as theory predicted. But the rate was wrong. Theoretical calculations based on detailed models of the sun's interior, the fusion reactions in the core, the energy generation, the temperature, the density predicted that Davis should detect roughly 7.5 solar neutrino units. A solar neutrino unit, or SNU, is defined as 10 to the negative 36 captures per target atom per second. It is a measure of interaction rate tailored specifically for solar neutrino experiments. 7.5 SNU, that was the prediction. Davis measured 2.5 SNU, 1/3. 2/3 of the expected neutrinos were missing. At first, the reaction was skepticism. Physicists questioned Davis's methods. The extraction efficiency, was it really as high as he claimed? Maybe he was losing argon atoms during the chemical separation. Maybe his proportional counter was not detecting all the decays. Davis tested everything. He injected known quantities of argon-37 into the tank and ran the full extraction procedure. Recovery rate consistently above 90%. The chemistry worked. He calibrated his proportional counter with radioactive sources. Detection efficiency confirmed. He checked for background sources of argon-37. Natural radioactivity in the rock, cosmic ray muons that penetrated to the detector depth, contamination in the perchloroethylene itself. Every background was accounted for. Every systematic error was quantified. The deficit was real. Other physicists turned their attention to the solar models. Maybe the core temperature was lower than calculated. The rate of certain fusion reactions, particularly the ones that produce the highest energy neutrinos, is extremely sensitive to temperature. A reduction of just 10% in core temperature could reduce the high-energy neutrino flux by a factor of 10 or more. But lowering the core temperature created other problems. The sun's luminosity, the amount of energy it radiates into space, is precisely measured. If the core temperature were significantly lower, the sun would not be producing enough energy to shine as brightly as it does. You could not adjust the solar model to match Davis's neutrino measurements without breaking the agreement with the sun's observed luminosity. The models were robust. Decades of refinement had gone into them. They predicted not just the luminosity, but the sun's radius, its surface temperature, the spectrum of its light, and even the frequencies of acoustic oscillations that propagate through the solar interior. Helioseismology, the study of these oscillations, had confirmed the solar models to extraordinary precision. The speed of sound at different depths in the sun matched predictions to within 1%. If the models were that accurate about the sun's structure, how could they be wrong by a factor of 3 about the neutrino flux? The solar neutrino problem became a wound in physics that would not heal. Not a crisis exactly, not a collapse of confidence, but a persistent nagging discrepancy that refused to go away no matter how many times people checked the calculations. For Davis, it was worse, because the discrepancy made people doubt him. Not loudly, not publicly for the most part, but in the quiet conversations at conferences, in the footnotes of papers, in the unspoken assumptions of review panels allocating funding. Maybe Davis was wrong. Maybe his detector was not working as well as he thought. Maybe the whole enterprise was flawed. Year after year, he published his results. Year after year, the number stayed around 2.5 SNU, one-third of the prediction. Colleagues suggested he was measuring background, that the signal was not from solar neutrinos at all, but from some other source he had not properly accounted for. Davis checked again, and again, and again. The extraction efficiency remained above 90%. The backgrounds remained small. The signal persisted. He was measuring solar neutrinos. He was certain of it. But 2/3 of them were missing, and no one could explain why. This is frustrating. It was deeply frustrating for Davis, for solar physicists, for theorists trying to understand neutrinos. Major questions do not resolve in months or years. Sometimes they require decades. Patience is not just a virtue. It is the method by which the universe reveals itself. In the late 1960s, a theoretical possibility emerged. An Italian-Russian physicist named Bruno Pontecorvo, who had worked with Fermi in the 1930s before defecting to the Soviet Union in the 1950s, proposed a radical idea. What if neutrinos could change, not decay, not transform into other particles permanently, but oscillate, switch back and forth between different types? At the time, only 2 types of neutrinos were known, the electron neutrino and the muon neutrino. The tau neutrino would not be discovered until the year 2000. But even with just 2 types, Pontecorvo realized something profound. If the electron neutrino and the muon neutrino had different masses, even slightly different, then quantum mechanics predicted a strange phenomenon. A neutrino created as a pure electron neutrino would not remain a pure electron neutrino as it traveled through space. It would be a quantum superposition, a mixture of the 2 mass states corresponding to the 2 flavors. As the neutrino propagated, these mass states would evolve at slightly different rates because they have different masses. The phase relationship between them would shift, and this shifting phase relationship would cause the probability of detecting the neutrino as an electron neutrino versus a muon neutrino to oscillate. At some distance, the neutrino would be mostly electron flavor. At another distance, mostly muon flavor. At yet another distance, back to electron. The oscillation length, the distance over which the neutrino cycled through its flavors, depended on the difference in mass squared between the 2 types and on the neutrino's energy. For solar neutrinos with energies around 1 million electron volts and tiny mass differences, the oscillation length could be on the order of hundreds of kilometers to thousands of kilometers. The sun is 93 million miles away, 150 million kilometers. Plenty of distance for oscillations to occur. If Pontecorvo was right, if neutrinos oscillated, then electron neutrinos produced in the sun's core could transform into muon neutrinos during their journey to Earth. Davis's chlorine detector only responded to electron neutrinos. It was blind to muon neutrinos. If a significant fraction of the electron neutrinos transformed before reaching the detector, Davis would measure a deficit, not because the neutrinos disappeared, but because they changed costume. The hypothesis was elegant, beautiful even. But it required something the standard model of particle physics said could not be true. It required neutrinos to have mass. The standard model as formulated in the 1960s and 70s assumed neutrinos were massless, like photons. No rest mass, just energy and momentum. If neutrinos were massless, oscillation could not occur. all the flavor states would be identical. There would be no differential evolution, no phase shifts, no transformation. Oscillation only works if the different neutrino types have different masses. So Pontecorvo's hypothesis was not just a solution to the solar neutrino problem. It was a prediction that the standard model was incomplete, that the textbooks were wrong, that there was deeper structure to the universe than we had yet understood. Most physicists in the 1970s considered this unlikely. The standard model was successful beyond anyone's expectations. It predicted the existence of particles before they were discovered. It unified the electromagnetic and weak forces into a single electroweak theory. It explained a vast range of phenomena with extraordinary precision. The idea that it was missing something as fundamental as neutrino mass seemed far-fetched, but the solar neutrino deficit persisted. And as the years passed, as Davis ran cycle after cycle, extraction after extraction, measurement after measurement, and the number stayed stubbornly at 1/3, a few physicists began to take oscillations seriously. If it was real, you would need a different kind of detector to prove it. A detector that could see all neutrino flavors, not just electron neutrinos, but muon and tau neutrinos as well. A detector that could measure the total neutrino flux from the sun and compare it to the flux of electron neutrinos alone. If oscillation was happening, the total flux should match the solar model predictions exactly. All the neutrinos would be there, just not all of them in electron flavor. Such a detector did not exist in the 1970s or the 1980s. The technology was not ready. The funding was not available. The theoretical case was not strong enough to justify the enormous expense. Davis kept running his experiment. 1975, 1980, 1985, 1990. The number never changed. 2.5 SNU, sometimes a bit higher, sometimes a bit lower, but always around 1/3 of the prediction. For 20 years, Raymond Davis published measurements that most of the physics community thought were probably wrong. For 20 years, he endured skepticism, doubt, and quiet dismissal. For 20 years, he climbed down into that mine, ran his extractions, counted his argon atoms, and trusted his data. He was 70 years old in 1984, 75 in 1989. Most scientists retire long before then. Davis kept working, not because he was stubborn, though he was, not because he had nothing else to do, though the experiment had consumed his professional life, but because he knew he was right. The measurements were correct, the deficit was real, and someday someone would figure out why. You have spent 60 minutes now following this story, following Pauli's desperation, Fermi's theory, Rayleigh's and Cowan's detection, Davis's decades of patient measurement. You have been given time because the scientists took time, because understanding does not come quickly, because the universe reveals its secrets to those who wait. And then in the early 1990s, the detectors that could solve the mystery finally began to take shape. Not in the United States, but in Japan and in Canada. Built by a new generation of physicists who had grown up reading about the solar neutrino problem in textbooks, who had studied Davis's measurements and wondered what they meant, who decided to build experiments large enough, sophisticated enough, and sensitive enough to see what Davis could not, to catch neutrinos in the act of changing, to prove that the ghost could wear different masks. The hunt was about to end. The revelation was about to begin. And Raymond Davis, 77 years old in 1991, would live to see it. The truth had been there all along, not hidden, not concealed by some conspiracy of nature, simply waiting for the right instruments, the right questions, the right minds willing to look in a different way. Raymond Davis had been right for 30 years. Every measurement, every extraction, every argon atom counted in that proportional counter deep in a South Dakota mine. All of it correct. The solar neutrinos were not missing. They were transforming. And proving that required detectors of a scale and sophistication that had seemed like science fiction when Davis began his work. By the early 1990s, they were becoming science fact. The first was being built in Japan. Deep beneath Mount Ikeno in the Japanese Alps, in the Kamioka Mining and Smelting Company's Mozumi mine, a cavern was being excavated. 1,000 meters of rock overhead. Isolation from cosmic rays. Silence broken only by the drip of groundwater and the hum of ventilation systems. The detector was called Super Kamiokande, Super K for short. Its predecessor, Kamiokande, 2 had already made history in 1987 by detecting neutrinos from supernova. 1987, a massive star that exploded in the Large Magellanic Cloud 168,000 light-years away. 12 neutrinos captured in 13 seconds, the first neutrinos ever detected from a stellar collapse. But Super K, would be different, larger, more sensitive, capable of studying neutrinos from multiple sources with unprecedented precision. The detector was a cylindrical stainless steel tank, 40 meters in diameter, 40 meters tall, filled with 50,000 metric tons of ultra-pure water. 50,000 tons. To put that in perspective, if you filled an Olympic swimming pool, it would hold about 2,500 tons of water. Super K held the equivalent of 20 Olympic pools, all of it purified to remove essentially every trace of dissolved minerals, radioactive contaminants, or organic compounds. Because even a tiny impurity could produce spurious light signals that would drown out the faint flashes from neutrino interactions. Lining the inner walls of the tank floor ceiling sides were 11,186 photomultiplier tubes, each one 50 centimeters in diameter, each one capable of detecting a single photon of light. They stared inward at the water from every direction, watching, waiting. The detection principle was Cherenkov radiation. When a charged particle travels through water faster than the speed of light in water, which is about 75% of the speed of light in vacuum, it produces a cone of faint blue light. This is the optical equivalent of a sonic boom. A jet traveling faster than the speed of sound in air, it creates a shock wave of compressed air that we hear as thunder. Similarly, a particle traveling faster than the local speed of light in a transparent medium creates a shock wave of light, a cone of photons spreading out behind it. No law of physics is violated. Nothing is exceeding the speed of light in vacuum. But light travels slower in water than in vacuum, and a high-energy charged particle can exceed that reduced speed. When a neutrino interacts with a water molecule, an event that happens only a handful of times per day, even in 50,000 tons, it can produce a charged particle, either an electron or a muon depending on the neutrino's flavor. If that particle is energetic enough, it emits a cone of Cherenkov light. The photomultiplier tubes detect this faint ring of light. From the pattern, the shape of the ring, its brightness, its position on the detector walls, physicists can reconstruct the direction the neutrino came from, its energy, and critically its flavor. An electron produces a fuzzy ring. Multiple scattering in the water blurs the pattern. A muon produces a sharp ring, cleaner, more defined. The detector can tell them apart. This meant Super K could distinguish electron neutrinos from muon neutrinos. It could measure both. Compare them. Look for discrepancies. Construction was completed in 1995. Data collection began in April 1996. The lead scientist was Takaaki Kajita, a Japanese physicist then in his mid-30s. Quiet, methodical, possessed of the same patient stubbornness that had defined Davis's career. Kajita was not interested in solar neutrinos. Not initially. He was studying atmospheric neutrinos. These are neutrinos produced when cosmic rays from deep space high-energy protons accelerated in supernova remnants, pulsars, or other violent astrophysical processes strike atoms in Earth's upper atmosphere. The cosmic ray protons slam into nitrogen and oxygen nuclei at altitudes of 15 to 35 kilometers. The collisions create cascading showers of secondary particles. Among them, pions and kaons, unstable particles that quickly decay. And many of their decay products include neutrinos. Muon neutrinos primarily. These atmospheric neutrinos rain down on Earth continuously. From every direction in the sky, some are produced in the atmosphere directly above the detector. They travel downward through just a few dozen kilometers of air to reach Super K. Others are produced on the opposite side of the planet. They travel downward through the atmosphere. They're then passed through the entire Earth, 12,700 kilometers of rock mantle and molten iron, and arrive at the detector from below. For atmospheric neutrinos, this distinction matters, because the distance traveled is vastly different. Downward neutrinos may be 30 kilometers through atmosphere. Upward neutrinos 30 kilometers through atmosphere, plus 12,700 kilometers through Earth. If neutrinos do not oscillate, both groups should arrive at the detector in equal numbers. The production rate is the same in all directions. The atmosphere is equally thick everywhere, and neutrinos pass through Earth without difficulty. But if neutrinos oscillate if they transform during flight, then distance matters. The longer the journey, the more time for oscillation to occur. Kajita and his team began analyzing the atmospheric neutrino data in 1996. They sorted events by direction, downward versus upward. They measured the ratio of muon neutrinos to electron neutrinos in each group. For downward neutrinos, the ratio matched expectations. Roughly 2 muon neutrinos for every electron neutrino, consistent with the known decay patterns of pions and kaons. For upward neutrinos, the ones that had traveled through Earth, the muon neutrino count was significantly lower. Not gone, not vanished, but reduced. The deficit was striking, unambiguous. Downward muon neutrinos expected rate. Upward muon neutrinos roughly half the expected rate. The farther the neutrinos traveled, the more of them disappeared, or rather transformed, because the electron neutrino count did not change. The total number of neutrinos seemed to be conserved. Only the flavor ratio was different. Kahita checked everything: detector systematics, event reconstruction algorithms, background contamination, statistical fluctuations. The asymmetry persisted. By early 1998, the evidence was overwhelming. Muon neutrinos were oscillating, transforming into tau neutrinos during their journey through Earth. Super K could not easily detect tau neutrinos with its current setup, so the transformed neutrinos were invisible. They appeared as a deficit, but the pattern matched oscillation theory perfectly. The oscillation length, the distance over which neutrinos cycled through their flavors, depended on the difference in mass squared between the muon neutrino and the tau neutrino and on the neutrino energy. For atmospheric neutrinos with energies around 1 giga-electron volt and a mass squared difference of about 2.5 times 10 to the minus third electron volt squared, the oscillation length was roughly 500 kilometers. Neutrinos traveling 30 kilometers, minimal oscillation. Neutrinos traveling 12,000 kilometers, substantial oscillation. The data fit the theory. On June 5, 1998, Takaaki Kajita stood before an audience of physicists at the Neutrino 98 conference in Takayama, Japan. He presented Super Kamiokande's results. Atmospheric neutrino anomaly. Deficit in upward-going muon neutrinos, consistent with oscillation. And then he said the words that would change physics. We have observed neutrino oscillation. Neutrinos have mass. The room erupted, not with applause, not yet, but with the sudden electric tension of a community realizing that something fundamental had just shifted. If neutrinos oscillate, they must have mass. That was not speculation. That was quantum mechanical necessity. And if neutrinos have mass, the standard model of particle physics, the theoretical framework that had been constructed over 4 decades that had predicted the W and Z bosons, the top quark, the gluon, was incomplete. Not wrong, incomplete. There was physics beyond the standard model. New structure, new mysteries. The textbooks would need to be rewritten. But Kahita's result did not directly solve the solar neutrino problem. Super K studied atmospheric neutrinos. Muon neutrinos transforming into tau neutrinos over distances of thousands of kilometers. The solar neutrino problem involved electron neutrinos from the sun traveling 93 million miles. And Davis's deficit suggested that electron neutrinos were transforming into something else. But Super K's atmospheric data did not tell you what. To definitively solve the solar neutrino problem, you needed a detector that could measure all 3 neutrino flavors. A detector that could say, here is how many electron neutrinos arrived. Here is how many muon neutrinos arrived. Here is how many tau neutrinos arrived. Here is the total. And compare the total to the solar model predictions. If the total matched every neutrino was accounted for, the sun was producing exactly as many neutrinos as theory predicted. They were just changing flavor en route. That detector was being built in Canada. The Sudbury Neutrino Observatory, SNO, 2,000 meters underground in the Creighton Mine near Sudbury, Ontario, a working nickel mine operated by the mining company Inco, the deepest underground laboratory in North America. The detector design was ingenious. At its heart was 1,000 metric tons of heavy water. Water in which the ordinary hydrogen atoms with a nucleus containing 1 proton are replaced by deuterium. Deuterium is an isotope of hydrogen whose nucleus contains 1 proton and 1 neutron. Heavy water is rare, expensive, difficult to produce. The 1,000 tons at SNO had been borrowed from Canada's nuclear industry, where it is used as a moderator in CANDU reactors. The value was roughly 300 million Canadian dollars. It was kept in a 12-meter diameter acrylic vessel, the largest acrylic structure ever built at the time. Transparent spherical suspended in the center of a much larger cavity filled with ordinary ultra-pure water. Surrounding the whole assembly were 9,600 photomultiplier tubes watching for Cherenkov light. The brilliance of heavy water is that it gives you 3 detection channels, 3 different types of neutrino interactions. First, the charged current reaction. An electron neutrino interacts with a deuterium nucleus. The weak force transforms one of the neutrons into a proton. The deuterium becomes 2 separate protons. An electron is emitted. This reaction is sensitive only to electron neutrinos. Muon and tau neutrinos cannot trigger it because they would produce the muons or tau particles, which are too heavy to be created by the low-energy solar neutrinos. Second, the neutral current reaction. A neutrino of any flavor electron muon or tau interacts with a deuterium nucleus and breaks it apart into a free proton and a free neutron. The neutrino bounces off and continues on its way. The free neutron is eventually captured by another nucleus producing a detectable gamma ray. This reaction is equally sensitive to all three flavors. It measures the total neutrino flux regardless of flavor. Third, elastic scattering. A neutrino bounces off an electron, giving the electron a kick. The electron recoils and produces Cherenkov light. All three flavors can do this, but electron neutrinos do it more readily than muon or tau neutrinos because of an additional interaction diagram available only to electron neutrinos. So elastic scattering is sensitive to all flavors, but predominantly to electron neutrinos. By measuring all three channels simultaneously, SNO could determine how many electron neutrinos arrived, how many total neutrinos arrived, whether they matched. The experiment began taking data in May 1999. The lead scientist was Arthur MacDonald, a Canadian physicist early 60s with a reputation for meticulous experimental work and an almost obsessive attention to systematic uncertainties. MacDonald knew what was at stake. If the total neutrino flux matched solar model predictions, Davis was vindicated. The sun was fine. Neutrino oscillation was real. If the total flux was also low, something was wrong with the sun, or with our understanding of fusion, or with neutrinos in some way that oscillation did not explain. The analysis took time: background subtraction, detector calibration, event reconstruction. Month by month, the data accumulated. By mid-2000, the pattern was emerging. The charged current measurement showed a deficit, only about 1/3 of the predicted electron neutrino flux, exactly what Davis had been measuring for 30 years. But the neutral current measurement, the one sensitive to all flavors, showed the full predicted flux. Every neutrino the sun was supposed to produce was arriving at Earth, just not all of them in electron flavor. In June 2001, Arthur MacDonald presented SNO's results at the Neutrino 2001 conference. The total neutrino flux from the sun, consistent with solar model predictions to within experimental uncertainties. The electron neutrino flux, 34% of the total. The remaining 66% muon and tau neutrinos. The solar neutrino problem was solved, not by fixing the solar models, not by correcting Davis's measurements, but by discovering that neutrinos change. Electron neutrinos produced in the sun's core oscillate during their 8-minute journey to Earth. By the time they arrive, 2/3 have transformed into muon or tau neutrinos. Davis's chlorine detector could only see the 1/3 that remained in electron flavor. SNO saw all of them. Every single neutrino predicted by the solar models was accounted for. The sun was fine. Nuclear fusion was understood. Stellar physics was intact. And neutrinos, those ghostly particles that barely interact with anything, had revealed themselves to be more complex, more subtle, more fascinating than anyone had imagined. They had mass. They oscillated. And the Standard Model, successful as it was, had missed this fundamental property. In October 2002, the Nobel Prize in Physics was awarded jointly to Raymond Davis and Masatoshi Koshiba for pioneering contributions to astrophysics, in particular for the detection of cosmic neutrinos. Davis was 88 years old. He traveled to Stockholm with his family, walked onto the stage in the Stockholm Concert Hall, accepted the medal and diploma from the King of Sweden. In his Nobel lecture, he spoke about the homestake experiment, the decades of measurements, the deficit that would not go away. He did not say, "I told you so." He did not express bitterness about the years of doubt, the skepticism, the quiet dismissals. He simply presented the science, the methods, the results. And at the end, he acknowledged the solution. Neutrino oscillation, the work of Super Kamiokande and SNO. For 30 years, he said, we measured 1/3 of the predicted flux. We did not know why. Now we do. The audience, physicists, dignitaries, Nobel laureates from decades past rose to their feet because they understood what this represented. Not just a scientific discovery, but a testament to patience, to stubbornness, to the courage required to believe your data when the world tells you you are wrong. Davis had been right. Every measurement for 30 years. The neutrinos were not missing. They were wearing different masks. And catching them in the act of changing, proving that this invisible transformation actually occurred, required detectors that filled caverns with tens of thousands of tons of ultra-pure water lined with thousands of photomultiplier tubes buried kilometers underground. It required the work of hundreds of physicists, decades of effort, hundreds of millions of dollars in funding. But it worked. The ghosts revealed their secret. The Nobel Prize in Physics for 2015 was awarded to Takaaki Kajita and Arthur MacDonald for the discovery of neutrino oscillations, which shows that neutrinos have mass. Kajita and MacDonald, Super Kamiokande and SNO, the experiments that proved what Davis's measurements had hinted at for 3 decades. In their Nobel lectures, both Kajita and MacDonald acknowledged Davis, the pioneer who had kept measuring, kept believing, kept extracting argon atoms from cleaning fluid in a South Dakota mine, even when the physics community doubted him. Davis had died in 2006 at the age of 91. He lived long enough to see his vindication, long enough to see neutrino oscillation confirmed beyond any doubt, long enough to know that his life's work had not been in vain. But the story does not end there, because discovering that neutrinos oscillate and have mass opens new questions. What are the actual masses? We know the differences in mass squared between the 3 flavors, but not the absolute mass of any individual flavor. We know at least 2 of the 3 have non-zero mass. But how much are we talking about? A millionth of an electron volt? A tenth a whole electron volt? Current limits suggest the sum of all 3 neutrino masses is less than about 1/10 of an electron volt. The electron, the lightest commonly discussed particle, has a mass of 511,000 electron volts. Neutrinos are at minimum several million times lighter than an electron. They are the lightest known massive particles in the universe, and we still do not know their exact masses. Another question, what is the mass ordering? Is the electron neutrino, the lightest with muon and tau neutrinos, progressively heavier? This is called the normal hierarchy. Or is the electron neutrino actually the heaviest with the other 2 lighter, the inverted hierarchy? The answer matters for cosmology, for models of the early universe, for our understanding of how neutrinos fit into the larger structure of particle physics. Experiments are being built to answer this. Juno in China, Dune in the United States, next-generation detectors with even greater sensitivity and precision. Then there is the question of whether neutrinos are their own antiparticles. Every other known fermion, every quark, every charged lepton is distinct from its antiparticle. An electron is not a positron. A proton is not an antiproton. But neutrinos are unique among known fermions because they carry no electric charge. And with no charge to distinguish them, it is possible that the neutrino and the antineutrino are the same particle. Such particles are called Majorana fermions, after the Italian physicist Ettore Majorana, who proposed the concept in 1937 before mysteriously disappearing at age 31. If neutrinos are Majorana particles, it would have profound implications. It would suggest a new mechanism for generating neutrino mass, different from the Higgs mechanism that gives mass to other particles. And it might explain one of the deepest mysteries in cosmology, why the universe exists at all. The Big Bang should have produced exactly equal amounts of matter and antimatter. When they meet, they annihilate. The universe should contain nothing but diffuse radiation. But somehow there was an imbalance. Roughly 1 extra matter particle for every billion matter-antimatter pairs. That tiny excess, that 1 in a billion asymmetry, is everything. Every atom in the universe. Every star, planet, galaxy, living thing. All of it is the leftover sliver that survived annihilation. Something created this imbalance. Physicists call the required conditions the Sakharov conditions, after the Russian physicist Andrei Sakharov, who identified them in 1967. One requirement is CP violation, a difference in how the laws of physics treat matter versus antimatter. CP violation has been observed in the quark sector, but the amount is far too small to account for the matter-antimatter asymmetry. Something else must be contributing. Neutrinos might be that something else. If there is significant CP violation in the neutrino sector, if neutrinos and antineutrinos oscillate differently, it could have influenced the balance of matter and antimatter in the early universe through a mechanism called leptogenesis. Heavy Majorana neutrinos in the first fractions of a second after the Big Bang could have decayed in a CP, violating way, producing slightly more leptons than antileptons. This lepton asymmetry could then have been converted into a baryon asymmetry, more protons and neutrons than antiprotons and antineutrons, through processes that interconvert leptons and baryons. The result, the tiny matter excess that became everything. Dune, the deep underground neutrino experiment, is being built specifically to search for CP violation in neutrino oscillations. A beam of neutrinos will be fired from Fermilab in Illinois to a massive liquid argon detector 1,300 kilometers away in the Sanford Underground Research Facility in South Dakota, the same mine where Raymond Davis ran his chlorine detector. By comparing how neutrinos and antineutrinos oscillate over that distance, Dune will measure whether there is a difference, whether the universe treats them differently. If it finds significant CP violation, it would be a major step toward understanding why anything exists. It would not prove leptogenesis by itself, but it would show that the neutrino sector has the right properties to make leptogenesis work. It would suggest that the reason you exist, the reason there are atoms and stars and planets and people might trace back to a subtle asymmetry in the behavior of the universe's most ghostly particle. And then there is IceCube, a detector unlike any other, located at the Amundsen-Scott South Pole Station in Antarctica. Not in a mine, not in a cavern, but embedded in the Antarctic ice sheet itself, 5,160 digital optical modules, basketball-sized glass spheres containing photomultiplier tubes strung along 86 vertical cables at depths ranging from 1,450 to 2,450 meters below the surface. The instrumented volume 1 cubic kilometer of ice. 1 full cubic kilometer. IceCube detects neutrinos at energies far beyond what Super K or SNO can reach. Not million electron volt solar neutrinos. Not giga electron volt atmospheric neutrinos, but tera electron volt and peta electron volt neutrinos. Energies a million to a billion times higher than solar neutrinos. These are cosmic neutrinos, produced by the most violent processes in the universe. Supernova remnants, active galactic nuclei, blazars with relativistic jets of matter and energy pointed almost directly at Earth. At these extreme energies, the neutrino interaction cross-section is much larger than at solar energies, which makes detection feasible, even though the flux of such high-energy neutrinos is far lower. In 2013, IceCube announced the detection of 2 neutrinos with energies exceeding 1 peta electron volt, 1 quadrillion electron volts. The collaboration affectionately named them Bert and Ernie. These were the highest energy neutrinos ever observed, each carrying roughly 1 million times more energy than any neutrino produced by a particle accelerator on Earth. Their origin was clearly astrophysical. They came from somewhere out there, from processes of extreme violence and power. Then in September 2017, IceCube detected a high-energy neutrino and quickly sent out an alert to observatories around the world. Telescopes across the electromagnetic spectrum, gamma-ray, X-ray optical radios swiveled to look at the patch of sky the neutrino had come from. What they found was a blazer. A galaxy roughly 4 billion light-years from Earth, with a supermassive black hole at its center, shooting a jet of relativistic matter and energy almost directly toward us. The blazer designated TXS0506 plus 056 was in a flaring state, producing intense gamma radiation. The neutrino had come from this blazer. For the first time in history, a high-energy cosmic neutrino had been traced to a specific astrophysical source outside our solar system. This was the birth of high-energy neutrino astronomy, using neutrinos not just as tools to study particle physics or the sun, but as messengers to observe the universe itself. Photons have been our primary astronomical messenger for all of human history. Gravitational waves, first detected in 2015, added a second messenger. Neutrinos are the third, and they carry information that neither photons nor gravitational waves can provide because they emerge unscathed from environments so dense and violent that light cannot escape. The core of a collapsing star, the accretion disk around a black hole, the interior of a neutron star merger. Neutrinos are witnesses to events that would otherwise remain forever hidden. Right now, as you finish reading these words, 100 trillion neutrinos are passing through your body. Every single second, 65 billion from the sun. Products of fusion in the core born 8 minutes and 20 seconds ago. A few billion from Earth's atmosphere. Created by cosmic rays from distant supernovae colliding with nitrogen and oxygen above your head. A smaller number from nuclear reactors scattered across the continents. Antineutrinos from the fission of uranium from the beta decay of neutron-rich fragments. And 336 relic neutrinos per cubic centimeter of space, born in the first second after the Big Bang, cooled by cosmic expansion to a temperature of 1.95 Kelvin, minus 271 degrees Celsius, ancient beyond almost anything that exists. Witnesses to the universe at 1 second old. They surround you. They fill every cubic centimeter of space. They pass through every planet, every star, every galaxy. And essentially none of them interact with anything. Not because they are forbidden to, but because the probability is so vanishingly small that the entire material universe is functionally transparent. The photon from the sun's core takes 170,000 years to random walk to the surface. Shattered, absorbed, re-emitted. endlessly delayed by electromagnetic interactions. The neutrino produced in the same fusion reaction at the same instant in the same place exits the sun in 2 seconds. Same star, same matter. But the photon interacts electromagnetically. The matter is opaque. The neutrino interacts only through the weak force. The same matter is transparent. 170,000 years versus 2 seconds. The difference between a force that holds the world together and a force that barely knows the world exists. You will never feel a neutrino. 100 trillion pass through you every second, and you cannot sense even one. The electromagnetic force that builds your body has no hold on them. But you know they are there. You understand what they are, where they come from, why they pass through everything. You know that Wolfgang Pauli proposed them in desperation to save energy conservation, that Enrico Fermi gave them mathematics, that Frederick Reines and Clyde Cowan caught them from reactors, that Raymond Davis counted them from the sun and found only 1/3, that Takaaki Kajita saw them oscillate, that Arthur MacDonald proved all were accounted for just transformed. You know that they have mass, that they oscillate between flavors, that the standard model is incomplete. You know that they might explain why matter won its ancient war against antimatter, why the universe filled with atoms instead of emptiness. You know that they carry messages from the cores of distant stars from blazars billions of light years away from the first second after creation. In the quiet contest between a particle that ignores all matter and a mind that seeks to comprehend all reality, the mind wins. Not by stopping the neutrino, nothing can, but by knowing it, by measuring it, by using it to see the hidden fusion at the sun's core, the collapse of distant stars, the birth of the universe 1 second old, the ghost particle and the curious species. Both made of the same atoms, governed by the same laws. One passes through everything. The other understands everything. And somehow, improbably beautifully, they found each other. The hunt is over. The ghost is known. But the questions remain. And somewhere tonight in a laboratory deep underground or embedded in Antarctic ice detectors are watching, waiting for the next ghost to reveal itself, for the next impossible thing to become inevitable, for the universe to whisper one more secret to those patient enough to listen.